Welcome. In this video, we'll take a look at a few more sum and difference identity problems. We'll take a look at number 3 first with the tangent of 255 degrees. So if I wanted to go find this identity in its exact form, one way I can do this is to break this angle down, 255, into a sum of two angles. So the sum here that might be helpful, you can do it in a couple ways, but we'll use the tangent of 210 degrees plus 45 degrees, where our A here would be 210, B is going to be 45. So here we have the form of tangent of A plus B. So let's consider a couple things. First, we want to consider what the sum identity for the tangent function is. We see that on the left side of our graph, our examples here. We'll highlight it here in yellow. So when we come across a tangent A plus B, we have that identity to fill first. Tangent of A plus tangent of B divided by 1 minus the tangent of A times the tangent of B. So let's first find the tangent of each of these individual angles, and then we'll go to work with filling it in. So let's draw a picture here. To start, we first want an angle of 45 degrees, and we'd like its tangent. If I consider the tangent of 45 degrees, we know tangent's positive in this quadrant, and it happens to be just 1. Our sine and cosine are equal, so our tangent will be just equal to 1. And the second angle we want to consider is the 210 degree angle. So the 210 degree angle will be sitting in our third quadrant. And this 210 degree angle will have a reference angle here of 30 degrees. And so when we consider the tangent of 210, we'll notice that tangent is also going to be positive in the fourth quadrant. So this will behave the same as the tangent of 30 degrees. And so the tangent of 30 degrees or the tangent of 210, both are going to be the same. And this will happen to be the square root of 3 over 3. You can find that in our unit circle, tangent of either 210 or that's the same as tangent of 30 degrees, that reference angle. So these are the two that I'm going to be using, 1 and square root 3 over 2 for the tangent of 210. So let's rewrite this expression as the following. First, this expression we can rewrite first with the collection of tangents, tangent of A, which is tangent of 210, plus the tangent of B, which is 45. And you'll notice that the order here doesn't matter, 210 or 45, as long as we choose one to be A, one to be B throughout the whole problem. We'll divide this by 1 minus the product, tangent of 210, tangent of 45. And we know the values of these results, so we just need to place them where they belong. So tangent of 210, we're square root 3 over 3. We'll have plus 1. And then we'll do divide by 1 minus the square root 3 over 3 times 1. One more thing that we could do to just simplify this expression just a little bit more is we can multiply on the top and bottom by a factor of 3 and distribute that through this expression. And when we do so, we'll get square root of 3 and then plus 3. and then we'll get 3 and minus the square root of 3. And for our purposes here, we'll just keep that as our solution here. So that's our exact solution. Let's take a look at a second example with some radians. We'll do the cosine of pi over 12 to look at a radian example. The principles are still the same. We just want to recognize, again, either a sum or difference that can get us to the pi over 12 angle. So this might be a helpful time to develop a little bit of a table for pi 12ths or any angle with a denominator of 12. So our common angles that we usually use are going to be pi over 6, pi over 3, pi over 4. I guess I can write these in descending order. Pi over 4, pi over 3, and pi over 2 is the 90 degrees. So if we consider these in terms of the denominator of 12, we could rewrite these as 2 pi 12ths and 3 pi 12ths, 4 pi 12ths, and 6 pi 12ths. Looking at them in this fashion can give us a good idea of what combination we're going to need for a pi over 12. It looks like 3 pi over 12 and 4 pi over 12, if I subtract them, their difference is going to be a pi over 12. So I could rewrite this expression as cosine of 4 pi 12ths minus 3 pi 12ths, which I know is equivalent to pi over 3 and minus pi over 4. Or we could represent those as 60 and 45 degrees. So remember that these are 45 degrees and 60 degrees if we're in degree mode. So we'll carry this through with some radian calculations just so we get used to working with those. So I have my A and my B angle. I'm looking for the difference of cosines in this one. So difference of cosines will come up here to find that equation. And I'll highlight this in the bright green. The difference of cosines is the first on the top of the right. So let's highlight that one. Difference of cosines is going to go cosine A, cosine B, plus sine A, sine B. So let's do that combination. Cosine A, cosine B is first. So we'll have cosine A, cosine B, and then plus sine A, and the sine is pi over 3, and sine B, pi over 4. Okay, so notice we're just following the pattern there set out by our difference of cosines in the bright green there. So let's finish off this problem with our expression now. So we'll have the cosine of pi over 3, that's the cosine of 60 degrees. That will be just 1/2 times the cosine of pi over 4. We know that to be just the square root of 2 over 2 plus the sine of pi over 3, or sine of 60 degrees, is the square root of 3 over 2. And then sine of pi over 4 is again going to be root 2 over 2. So we can finish this up. This will be square root 2 over 4 plus square root 6 over 4, or we can express that in one fraction, square root 2 plus square root 6, all over that common denominator of 4. So this is not the only combinations of angles that we could use. Notice that looking back at our little table, we could have used 3 pi over 6 and 2 pi over 6. That would have given you the same solution. But putting together this little set in this table is kind of a helpful deal when working with radian values when they have a denominator of 12. So hope this is helpful with these types of examples. We'll take a look at some more identities in the next video.